record on this computer. All right, we're recording. Cool. Hello, everyone. This is new walkthrough of the Vector final security walkthrough, internal security walkthrough of the Vector contracts. I guess the goal here is to go line by line through every contract, and then as we go along, we can kind of fill things in with some context. And then in this call, we won't actually be going over the protocols themselves, just like the contract implementation. So for the most part, we'll just assume that signed messages that are being passed into the adjudicator or into the channel master copy, kind of like the deposit withdraw code, are signed correctly within the protocol implementation itself. Cool. So getting started. So the first, we're going to work through like the lifestyle of the channel itself. So the best place to get started there is the channel factory. The goal behind the channel factory is we use a proxy pattern to deploy every single channel, and that way we reduce the gas costs of deployment. And then the channel factory is kind of the overarching code that stores the proxy bytecode and then kind of deploys it per channel. Cool. So bytes, proxy creation code prefix, proxy creation code suffix. What is this for?
Well, this is our proxy code.
This is the hard-coded proxy, right?
Yeah,
okay.
That's our proxy in bytecode. So yeah, well, it is taken from
the minimal proxy factory, which we deleted, I believe, but we should definitely comment the EIP that this was taken from. Yeah. So I'll find that right now.
Yeah, good idea.
Cool. Okay, so address immutable master copy, address immutable chain ID. In the constructor, we pass in the master copy and chain ID. We don't get the chain ID from the chain because this was kind of an edge case that we discussed internally. Basically, in some chain implementations, people don't implement the chain ID opcode correctly, and if let me turn off the solidity formatter so we're not. Because of that, because some chains implement the chain ID opcode incorrectly and actually set their chain ID as 1, we would end up running into like collisions, chain ID collisions between mainnet and like other non-Ethereum chains that don't respect the chain ID like format. So we decided the best thing to do is just to pass it in, and ideally, if we pass in 0, so basically if we don't explicitly pass in a chain ID, then we get it from on-chain. So going into the public methods, there's get master copy returns this master copy. Get chain ID returns recorded chain ID. Get stored chain ID returns just the chain ID that is stored. So basically, if we have passed in a 0 chain ID and we expect the chain ID to be provided from the on-chain chain ID opcode, then in that case, this would return 0, if I'm understanding this correctly. So then get proxy creation code. This returns the actual code, ABI encoded packed encoding of the prefix, the actual master copy address, and then the suffix. And this should be the proxy code that is used to deploy the proxy. And then get channel address. So we, as part of the protocol, we compute channel addresses beforehand, so we don't have to deploy the contract up front. And we can compute that using create2. Is this a create2 library?
This is from OpenZeppelin.
Oh, it's okay, got it. Nice. I'm glad we moved to that. So we use the OpenZeppelin create2 library to compute this address. We pass in a salt associated with both parties. Basically, it's the address of both parties, and then hash that against the proxy creation code, which comes from this get proxy creation code function. And then we can also create the channel. So creating the channel actually deploys this proxy. We deploy this deterministically using the setup function. So, okay, using the deploy channel proxy function, which I think is below. And then we call setup on the channel itself. So let's jump into deploy channel proxy, since that seems to be. So what this does is this generates the same salt that we had before up here, and then calls the OpenZeppelin create2 deploy function with the salt and the proxy creation code. So this will deploy using create2 to the same address that we generated in the get channel address function. The OpenZeppelin create2 library makes this a lot cleaner. I'm glad we switched to that. And then we have this separate convenience method, create channel and deposit Alice. So as part of the implementation, Alice basically deposits using a function on the channel contract itself, and then Bob just sends funds to the contract. And this is done for Bob's convenience. So Bob, as typically the end user, doesn't have to, doesn't really need gas, doesn't have to consciously think about depositing into the channel. He can just send funds whenever. And Alice, on the other hand, eats this slightly higher complexity of depositing, but that's fine because typically Alice is a router, a service provider that's always online anyway. So here we basically do what we do with create channel. We wrap the create channel method, and then in addition to that, within the same call, so we don't have to wait off chain, we also deposit from Alice's side. So there's a to do here. I don't know if this was cleaned up in the other branch, but basically what this is doing is it's creating the channel. We're then doing a transfer from. Interesting. Lib asset is Ether. Then we do lib ERC20 transfer from. And then otherwise we do. Oh, if it's not Ether. Okay, so if it's not Ether, basically we're doing a transfer from followed by an approve. So I guess is the assumption here that you've already approved the contract?
Yeah.
Yes.
Okay. So why is this structured this way?
So we are basically routing the funds through the factory. That is what is ugly and a bit inefficient because it's just a detour. But other patterns are problematic too because you have to approve to another contract, and then basically you always want to, after a transfer from, you always want to write message.sender.
Right.
So we had already discussed this a while ago. So everything else is a bit ugly too, because then you have to make the function permission so that only the factory can call it. So it's either way a bit ugly.
Right. I guess one thing that I'm wondering is, why is the approve here after the transfer from? Does this mean that we'll attempt to transfer from, and then if we can't, we'll just approve the asset first? And assume that the,
because that like transfers it from the user, like whoever's deploying it, to the channel factory. And then the channel factory approves the contract that it's going to deploy.
Yeah.
Got it. Okay. Yeah, that makes sense. Okay. Okay. So we should have a comment here.
Yeah, I'm adding notes as well. So if you don't want to take notes on this call, I can do that.
Okay, that's helpful. In that case, I'll just ignore this for now. But yeah, we should definitely have a comment here that explaining the way that the funds are routed to this channel factory, and then subsequently to the address. I wonder if, I mean, you can derive this address up front, right? So why can't you just approve the address directly, and then just call, like, basically don't skip this just by approving the address directly?
Because you do not want everybody to be able to call the function. You could approve wrong, you could transfer from wrong amounts. It's just a
Oh, I
problem
see.
with the general pattern of this. You always, you do not want to approve to someone else.
Okay. I mean, I guess that what you could do is just approve the exact amount, right? Like, for instance, Alice approves the exact amount. Basically, Alice calls get channel address, approves the exact amount that she wants to deposit to the channel address, then calls create channel and deposit Alice, which would do, channel equals create channel Alice Bob, and then subsequently would just call this deposit Alice, and then this deposit Alice function should internally transfer from the original, I guess, because you don't know the original address of Alice. I see. Okay, I see. That makes a lot more sense. So you do need message.sender context. Could you pass the message.sender along as part of this deposit call?
Well, you could do it somehow, but then you need to change the normally fully general deposit Alice function, or you would have to write a different one. And even then, it is still an ugly pattern if you want to rely on the fact that only a specific amount has been approved. This is always a bit frowned upon, so that's discouraged.
Okay. So, in that case, I think this makes sense. Cool. And then we have these internal methods, which we've kind of covered already. Jumping into, I guess from here, the best place to jump into is into the actual iVector channel, which is this channel master copy.sol. So this is just wrapping all of the other pieces, all of the mix-ins. So we should maybe the best place to start is the CMC core, and then we could jump into CMC deposit. CMC core. So I'm noticing that we have the CMC core as reentrancy guard here. Did we not? I guess we didn't end up doing the pattern where we had an intermediary contract because that wouldn't work in some cases. Is that correct?
Correct. Yeah, it did not work with view functions.
Okay, I see. So for context, one thing that we had attempted to do here, so in general, this channel master copy contract is an on-chain singleton, and then we deploy proxies to it, right? So because we're deploying proxies to it, all calls are routed from the proxy to like delegate call from the proxy to this CMC core or the CMC contract. And one thing that we had considered was a blanket reentrancy protection, where we actually route to a middleware contract that just does that is just a reentrancy guard, and then forwards all calls subsequently to the CMC contract. However, we have view functions, and those would not work with that pattern. And so instead, we've elected to keep this reentrancy guard modifier within the CMC contract itself. This adds a little bit more complexity because we need to we basically need to manually set up the reentrancy guard and do things that we'll touch on in the future as part of calling these contracts. But at the moment, this seems to be the best solution. So jumping into CMC core, we store Alice and Bob's addresses internally. This is basically the channel initiator and the channel responder. These are different, and these are stored as different things because they behave slightly differently. And this is one of the core parts of how the contracts in the core protocol work, which is that we generally assume that Alice is a high fidelity user, i.e. Alice is like a routing node, some entity that can be online very frequently and is like generally has access to ETH for gas and generally has the ability to call contract functions. And then we assume on the other hand that Bob is a very low fidelity user, so it's an end user that may or may not have ETH for gas and is likely not going to be able to spend a bunch of time watching the chain, and also most importantly is able to deposit into this channel contract simply by sending funds. So channel master copy, we set this address as the channel master copy address. We have an only via proxy modifier, which ensures that this contract can only be called by the proxy itself, and that stops users from trying to call this CMC contract directly. And then we we have this setup function. So setup basically is the constructor that we use as part of setting up the proxy. It can only be called via the proxy, and we pass in Alice and Bob's address. And this gets called as part of the call from the channel factory. We saw this earlier over here when we're creating the channel. We call ivector channel.setup, and we pass in Alice and Bob's address. What this does is, first of all, ensures that this contract has not yet been set up. Secondly, requires that both Alice and Bob have valid participant addresses, i.e. that they have addresses to begin with, not passing in 0 addresses. We also check to ensure that Alice and Bob are not the same person. Doing this would definitely result in a, I mean, we would be taking care of this in the off-chain protocol, but it is helpful to have this check in here to ensure that nobody's abusing this contract by creating channels with themselves. Then we set up the reentrancy guard itself. We can jump into that in a second. And then we set Alice and Bob's addresses. Maybe we can jump quickly into the reentrancy guard. So what the reentrancy guard does is reentrancy guard setup sets this like global variable lock to open. And then we have 2 modifiers: non-reentrant, non-reentrant view. Non-reentrant requires that the lock is actually open, then locks it, does the whatever function that's being called, and then subsequently opens the lock back up. And then non-reentrant view simply requires the lock is open. Pretty basic stuff. We needed to use this as opposed to like out of the box reentrancy guards like Open Zeppelins, just because of the view calls themselves. Cool. Jumping back into CMC core. So after setting up the channel, in the case of the contract, in the case of the call that we made to do create channel and deposit Alice, we also subsequently call ivector channel.deposit Alice. Deposit Alice is a function. Actually, let me get through this first. So get Alice, get Bob, just explicit getters to return Alice and Bob's addresses. If we jump into CMC deposit, we have the deposit Alice function. So deposit Alice takes in an asset ID and amount. It checks to see if the asset ID that we are depositing with is Ether. So this deposit Alice could be called by the channel factory, though it doesn't always necessarily need to be called by the channel factory. If it's Ether, we check to ensure that the value that's submitted as part of this is equal to the amount. And then otherwise, we do a transfer from the sending address to this. So this will work with the channel factory because this will be called by the channel factory. So the message.sender will be the channel factory address, which would be the one that holds this. Is there ever any case where we need to worry about the fact that the channel factory is a on-chain singleton, which could potentially be holding a lot of funds if lots of people are calling, or not holding funds, but basically have within a single call could be holding funds. Is there ever any case that we need to worry about the fact that this is a singleton contract and this is, the proxy is not?
I don't think so. Funds are immediately passed on. So this happens within the same transaction. So funds never really stay there. They are just routed through.
Okay, so I guess that's good. Then if we never have to worry about the state, as long as we never have to worry about the state of this contract itself, because this contract should effectively be stateless too. Okay, so jumping back into this, we basically add the deposit amount to deposits Alice. So kind of an explanation behind this. We have a mapping on chain of the deposits that Alice has made. These are the total amounts that have been deposited by Alice, indexed by asset ID, and we can get this total deposits. Basically, get this from the mapping. The reason we do this is that off-chain, or at least as part of how the deposit works, we keep track of the total amount deposited by Alice and the total amount withdrawn in total between both parties. And then off-chain, we keep track of the processed amount, basically the processed deposit amount from Alice and Bob. Using the combination of those three variables and the current amount of, like basically the current balance of the contract, you can always explicitly calculate the total amount that has been deposited by Bob. So let's see if we have that here. Yeah, so lib asset get own balance, basically the on-chain balance plus the total amount that has been transferred within this contract. Basically, this is the total amount withdrawn, and then the total amount deposited by Alice would always be equal to the total deposits of Bob. And using this, we should always be able to calculate how much money is currently deposited to Bob that isn't a part of this off-chain state yet. We can jump into this a bit more in the adjudicator, but the idea here is that we want to enforce that we are using invariant on-chain properties to ensure that you can always figure out how much Bob has deposited, even if that deposit hasn't yet been reconciled on chain, or hasn't been reconciled in the off-chain state. And as part of this, we explicitly don't use safe math here. I'll kind of explain a little bit more. We can go into a little bit more about why this is in the adjudicator. Cool. I guess the next best thing is probably the withdraw, happy case withdraw, unless there's anything in the asset that we need.
Asset, yeah.
Okay. Let's see. Let's start with withdraw, and then we can go into asset. All of the happy case withdrawal code exists within this CMC withdraw.sol. The general strategy for a happy case withdrawal from the channel is that if both parties sign a commitment saying that they want to withdraw some funds or perform some action on chain, and that commitment is basically we would do some like basic replay protection to ensure that you can't actually reuse the same commitment repeatedly to withdraw repeatedly. So as long as that commitment passes the replay protection check, you should allow both parties to withdraw funds from the channel, or both or either party to withdraw funds from the channel. This is the happy case withdrawal. So in this case, there's a withdraw, like off-chain negotiation that happens between both parties to ensure that both parties are okay with the amount that is being withdrawn. So we have a validate withdraw data modifier. What this does is we pass in the actual call data of the withdrawal, and then we ensure that the channel address of this withdrawal is the same as the address of the proxy. And that way you can't replay withdrawal states across different channels. Then we have a get withdrawal transaction record. Basically, this checks to see if this withdrawal data has been executed yet. This is our replay protection. So we have a is executed mapping that takes in a hash, and then it's basically like a hash to a Boolean operator. And we check to see, we basically check to see if this withdrawal, the hash of this withdrawal data has actually been completed or has actually been executed as part of a previous withdrawal. And then we have the core withdrawal function. The core withdrawal function takes in the withdraw call data. It takes in signatures from both parties. We check to make sure that this is only coming in via the proxy and that this is a non-reentrant call. And we also validate the withdrawal data to ensure that this withdrawal data is associated with this channel. we generate a hash of the withdrawal data. We verify both signatures on that withdrawal data. We check to see if this withdrawal has already been executed. And if it hasn't, then we set the is executed to true. And then we determine the actual amount. So we can jump into that function in a second. And then actually, let's jump into that right now. Where is it? Okay, there we go. So get available amount takes in an asset ID and takes in max amount. Here, the max amount that we're passing in is the withdrawal amount. And then we return the minimum of the max amount and the balance of this contract. So effectively, this should check to make so in the event that both parties sign a withdrawal state off chain that is for more than the amount in this contract, they're still able to use this withdrawal state to defund, basically to remove up to the amount that they have signed for. Is that a good explanation?
Yeah, that's a good explanation. It's useful in any way, but the point is, the general idea is that our off-chain state is normally accurate. So this should, in a regular operation, it should not happen in the first place, that there's less in the SIG than what we believe there to be, and so this should normally this should work just fine. There is, however, the one single case that my counterparty, that I send a withdrawal commitment to my counterparty, which does not countersign it, but submits it to the chain at a later point. So we have to take into account that the balance on the chain could actually be less. So we have to deal with, although the very reason we are dealing with it is probably enough that it never really happens.
So the potential issue here is that, like, maybe a good way to say it is, like, the potential issue here is that Alice submits creates a withdrawal with Bob for 1 ETH, and then Bob, instead of countersigning that withdrawal commitment, holds the withdrawal commitment for now. He himself, or some other things happen within the channel, reducing the channel balance below 1 ETH. And then Bob subsequently submits that 1 ETH withdrawal amount on chain. And because he subsequently submits that commitment on chain, the commitment would be executed. So it wouldn't be possible for Alice to like resubmit it. Is that the issue?
Yeah, it's basically like safe withdrawal commitment submission after you defund transfers.
Okay. Oh, I see. Okay. So in the event of a dispute, you are still able to continue using your withdrawal commitment that has not yet been used.
I believe so.
Okay, got it. In general, I think we should try to do our best to enforce that if a withdrawal commitment is generated, you should submit it as fast as possible. But I see the case where it's like one party could withhold a signature to try to avoid having that happen.
Yeah, I mean, both parties get the data to submit it, like when the withdrawal is resolved out of the channel. So you would have to dispute the withdrawal transfer if, like, for example, they didn't submit it. And say you try and dispute that transfer and defund it, and then they try and submit it to chain, you're still covered.
Okay, got it. Okay, so then we have, maybe a good thing here then is we should have like a longer explanation around this in a comment that explains that specific case, because I think like we can have like an explanation of the actual withdrawal protocol flow and like the withdrawal flow in general and how we do that, and then but explaining that this is valuable in the event where you are in this intermediary place between where you haven't necessarily completed the withdrawal transfer, basically the withdrawal transfer definition has not yet, the conditions for that have not yet been met. But the counterparty does have a single signed state that they could use and that they have a free option with. Cool. So basically, we take the transferable amount. If there is nothing to transfer, so basically if the contract balance is 0, this becomes a no-op. And then if we have something to transfer, then we call the transfer asset helper. And then lastly, we call this withdrawal helper to execute. So let's take a look at the transfer asset helper. So transfer asset basically does takes in the asset ID, recipient amount, registers the transfer, and then requires that this is interesting. Okay, so registering the transfer takes this, basically it just adds this to the total transfer amount. So here we're just incrementing the total withdrawn amount so that it's so that it can be used in the event of a dispute. What does this require do?
This is just that the normal transfer succeeds, like you know it from the ERC20 transfer, that you also wrap in a require.
Okay, I see. What is
It's
this unregistered transfer function?
I deliberately called it unregistered transfer function. It is really just a transfer function that transfers either Ether or ERC20 token. So it's just a convenience wrapper. You don't have to boilerplate through, is this Ether or is this a token yourself? So, but I deliberately called it a little bit, I gave it a clumsy name so you don't use it accidentally, because you normally don't want to use it because you also have to register as a transfer. And if you do not do that, then your bookkeeping gets out of sync. So I gave it a clumsy name, so you know you don't want to use it normally.
Got it. So this is basically the lower level helper method that should be used internally to this lib, but
this is
we don't want it to be.
This is really the only place probably where you ever want to use it.
Got it. Okay, that makes sense. Okay, and then we have verify signatures on withdraw data hash. So that gets called up here as part of checking the SIGs on the withdrawal data. Here we ABI encode the commitment, the actual withdrawal data itself. Or sorry. Yeah. So I always forget the actual ABI.encode method signature. What is is it the withdraw? Is this the actual structure, the actual encoding?
So this is just an enum. It could also be a string that says withdraw. This is just so you cannot use it in a different place. So it's just anchors it to the withdraw procedure, so to speak.
Got it. Okay.
We have something similar in the adjudicator. Yep. So these are the only two places where we verify signatures, but we want to give them a context so they cannot be used out of context.
Okay, makes sense. Cool. So we add context and hash it as part of this commitment. Then we check the commitment signature against both of these things. I think for commitment, we're using another helper lib, which is lib channel crypto. And we can jump into that in a minute. And that's basically it. And then we have this hash withdrawal data function, which just generates the hash of this withdrawal data. Quickly going to jump into lib channel crypto, since that'll be helpful everywhere. We have a check signature function that takes in a hash, memory, and alleged signer. I like that name. We check to see, basically we call the lower level recover channel message signer function and check to see if the signature derived from that is equal to the alleged signer. Recover channel message signer basically just does an Open Zeppelin ECDSA recover. And then the one other thing that we do is we when we're hashing the channel sign message, we have this IndraSign message prefix. We should probably change this to vector. There's a to-do here for it, but let's just do it. Let's do it now. Yeah,
it's gonna break all the tests, but yeah, I'll put a note up about it. We don't have to do it right now, but we can do it today.
Yeah. The good thing is like all of this is in libs now. Like there's the lib channel signer here, or lib channel crypto here, and then we have like the off-chain channel signer class. So it should be fairly easy to refactor this, or just to change this.
Oh yeah,
cool.
definitely.
Yeah. Okay, jumping back. So that was CMC deposit and CMC withdraw. So that's kind of like the happy case flow. It kind of to summarize, like to deposit, Alice calls the on-chain deposit Alice function, deposit A function, and then Bob just sends funds to the contract. We have a mechanism to ensure that in the event that in the event that you're calling deposit Alice, we manually iterate the total amount of value that has been deposited by Alice so far on chain, and then we have like a calculation, like an algorithm to figure out the total amount deposited by Bob based on the total amount deposited by Alice and the total amount withdrawn and the current balance of the contract. And that's something that we use as part of the actual adjudicator logic. So jumping into the adjudicator. So in the adjudicator, this is where like all of the dispute logic exists. So for any non-happy case flow, we like effectively any case where channel communication, off-chain communication breaks down, and users need to withdraw their funds and get their funds out of the channel, either get them out of a single transfer or get them out of the channel entirely, you would need to call adjudicator functions. So basically the goal with the adjudicator is we need to ensure that no matter what state the channel is in, no matter what action has been taken within the channel, we always have an exit pattern. And the really critical actions that can be taken that we need an exit pattern for are usually things around depositing, withdrawing, and then of course, removing funds for like individually removing funds for different transfers within that have not yet been resolved. Jumping into the actual implementation, we have this constant initial defund nonce. We set this to 1. This is something that we'll can cover in a little bit, but yeah. Then we have this channel dispute struct. Where is this actually defined? I'm assuming that this is in the interface.
ICMC adjudicator.
Okay, cool. So maybe quickly jumping into the actual structs here in the adjudicator interface. We have the core channel state. So this is the off-chain state of the channel. This is what will be passed into all of the adjudication logic. We have the core transfer state. This is the off-chain state of a given transfer that is as yet unresolved. In general, the core channel state is signed by both parties, Alice and Bob. And basically every update to the channel involves generating a new core channel state. And this core channel state is a commitment that gets put on chain in every dispute. We don't sign the core transfer state directly when the transfer exists. And the reason that we don't do this is that the hash of this core transfer state is actually a part of the Merkle root of all transfers within this core channel state. So that means that we can always prove that a transfer exists by doing a Merkle proof against this root. And then we have the actual dispute structs. So we have the channel dispute struct. In this case, we have basically this is registered as part of a new channel dispute. We register a hash of this state. As best as we can, we try to only store hashes on chain, which in like other kinds of simple things, which reduces gas costs. So we store the hash of this channel state, and then we would pass the channel state in on every call. We store the nonce of the dispute. This is the channel nonce. Basically, what version number of this core channel state have we reached? Should match this. We store the Merkle root, which would match the Merkle root in the core channel state. We store consensus expiry and defund expiry. So basically consensus and defund expiry are two time windows. We have like two windows within which the dispute occurs. We have when you dispute a channel, there is something called the consensus phase, and that is the phase within which you agree upon the latest. Both parties agree upon the latest core channel state on chain. And then once that window completes, you have the defund phase. And the defund phase is where you are now able to pull funds out of your channel, either out of your channel overall or out of an individual transfer. So those both get set when you create a channel dispute. We have a similar transfer dispute struct. In the transfer dispute struct, we have the transfer state hash, the transfer dispute expiry. Similar concept. There is a period of time after you dispute a transfer within which that transfer must be resolved, and if it isn't resolved by this expiry, then the current on-chain state is the one that quote unquote wins. That's the one that you go with. And then we have this is defunded bool to ensure that we can't redispute transfers after they have been disputed. And then we have a few events. So they're probably not too critical to go through right now. And then this is the actual interface. So jumping back into the adjudicator. Jumping back into the adjudicator, we have defund nonces. We can cover those in a minute, and transfer disputes, which we talked about just now in the interface. We have a validate channel modifier. This is similar to the modifier that was in, I think it was the CMC core, or was it in CMC deposit?
In the withdrawal.
Oh, it's in the withdrawal, sorry. Yeah, so this basically enforces that the core channel state, the channel address of the core channel state that's passed in is equal to the address of this channel, and that the Alice and Bob addresses are correct. And then we also have a validate transfer modifier, which also checks to see if the transfer state address is like the channel address in the transfer state is equal to the address of this proxy. Then we have a get channel dispute that returns. Basically, would this be the current dispute, or would this return? I guess this would return the channel dispute object, which would be the latest dispute that has occurred.
Yeah, we only store the latest dispute.
Okay, got it.
It's the current dispute information.
Okay. And then get defund nonces, get defund nonce. We can jump into that in a minute as well. Get transfer disputes does a similar thing. And then we get into the actual meat of the adjudication logic. So to start a dispute, the first thing that has to happen is you call dispute channel, and this starts the consensus phase of the dispute. When we call dispute channel, we pass in the core channel state, and we pass in Alice and Bob's signatures. And then this can only be called via the proxy. This is a non-reentrant call, and we validate that the address of this is equal to the address of the proxy. We generate the core channel state hash. Can jump into how this happens in a little bit. We verify the signatures on this hash, basically ensuring that that this is a valid state that both parties have signed. And then we check to make sure that this channel is not already in dispute. So it's not already within the defund phase. What this means is that this function can be called either when the channel is not in dispute or when the channel is in the consensus phase. And in the event that this is in the consensus phase, i.e. in the event that you're calling this when you and your counterparty are trying to decide on chain that this is the latest state, you would then register the new core channel state as the state that is on chain. And you would do this when the nonce is strictly greater than whatever is stored on chain as part of the actual channel dispute. What this means is that, like, if Alice disputes with channel nonce number 10, Bob is able to call the dispute for channel function within the same channel, within the same window, if he has a state number 11. And similarly, if Alice disputed with channel nonce 10 and then the dispute completed and then Alice and Bob went back to happy case functioning with each other, Bob at some point in the future could dispute again when the channel is not in dispute, so long as the new state that he has is at a higher nonce. Cool. And this is kind of where we get into that specifically in consensus phase logic. So if we're in consensus phase, not in consensus phase logic. So if we're not already in a dispute, that's when we would set expiries within the channel dispute struct. Effectively, we have like a timeout that's a part of this core channel state that we enforce off chain, and then we double that timeout for the actual defund expiry. Aside from that, all we do is we store the latest state on chain, and we emit this channel disputed event. Now this continues until this consensus expiry completes. So that's what this in defund phase function does. Is this in libutils? No. Excuse me. Where are the phase helpers?
They're at the bottom.
Oh, they're at the bottom. Okay. I don't know if they were in the same file. Cool. So yeah, basically in consensus phase checks to see if the consensus expiry has completed, and in defund phase does the same thing, checks to see that the consensus expiry is less than or equal to blocks timestamp, and so basically I guess this is accounting for the case where okay, yeah, so this is basically your the defund expiry has not yet expired, but the consensus expiry has expired. Cool. And then we have the same kind of hash channel state, hash transfer state helpers that we had before. Going back up here. So after this expiry is complete, after the consensus phase is over, you can no longer call dispute channel. Now the only thing that you can do is defund your channel. So the defund phase starts. You can defund your channel. You can defund individual transfers. Let's start with defunding individual transfers, since those are a little bit more isolated. When you dispute a transfer, you're kind of doing the same thing that you do when you dispute a channel. You pass in a core transfer state, and then you pass in the Merkle proof data instead of signatures. And because we have stored the Merkle root on chain, you don't need, I mentioned earlier, we don't sign the core transfer state. All you need is the Merkle proof data to prove that this transfer exists and funds are locked in it, and that you need to remove funds from it. So we check the transfer state hash, or we get the transfer state hash, and then we verify that hash is part of the Merkle root stored on chain, and we check to make sure that this is in the defund phase. Now, the reason that we need to make sure that the dispute transfer is only called within the defund phase is that we need to be completely sure when disputing a transfer that the on-chain Merkle root is the latest on-chain Merkle root available. So the consensus must already have been achieved on-chain on what the latest state is, which means that we can't actually begin disputing transfers until after the entire channel is in the defund phase. We get the stored dispute for this transfer. Let's see. What does this do? Where is this coming from? Transfer dispute. Oh, I see. This is the on-chain dispute, transfer dispute, like struct. So we basically get the struct associated with this transfer ID. This means that would there ever be a case where like this is non-zero? By non-zero, I mean like not initialized.
Or let's check for.
I think at this point it always is zero, but the point is we're reading it from storage, so we will later write to storage. So this is just,
right.
Just the solidity pattern. So we have a reference to storage, so to speak. And
right.
we save now gets actually written to storage, and we don't have it in memory.
Right.
That's what we're
so,
reading here.
The reason that I was asking that is that this is one kind of like key gotcha, or not gotcha, but like key difference between disputing a transfer and disputing a channel, where it's like when you're disputing a transfer, you don't have, it's not the same as disputing a channel where it's possible for the counterparty to submit a higher nonce state. When you dispute a transfer, the transfer state that you're submitting is the initial state of the transfer. And there are in general, there are only two states that a transfer could be in, which is the transfer has been initialized and it's been created, which means that it's a part of the Merkle root. And basically funds have been allocated to it. So the channel balance has effectively been reduced by the transfer amount. Or there is the resolved state where the transfer balance has already been reintroduced back into the channel state, and the transfer is no longer a part of the Merkle root. So what that means is that there is only one possible CTS that you could ever call this dispute transfer with, which means that this would always be this should always be zero. Like there should never be an already existing transfer dispute struct for this specific transfer ID. And if there is, then it should always be the case that this transfer dispute expiry is non-zero. So effectively, we should never be able to call dispute transfer for the same transfer multiple times, unlike with dispute channel. And that's kind of a simplification that we did because otherwise you end up with a state machine within the transfer in the same way that you have a state machine within the channel. And then the adjudication of that state machine, like progressing that state and adjudicating that state, ends up adding a lot of complexity to this implementation and to any channel implementation. In this case, we basically say that the protocol itself only cares about allocating funds to and deallocating funds from a given transfer, and whatever you do within that transfer is your own problem. You kind of need to figure that out yourself. That's a part of your off-chain implementation, and all we do is ensure that you have either some way to resolve it or you have some way to revert it in the event that you dispute without a resolving state. Cool. So we verify this transfer has not been disputed before. Then we set this we set this transfer data to this specific transfer dispute, and then we emit the transfer disputed event. Now, if a transfer has been disputed in this way, if a transfer has been basically has been proven on chain to be existing and unresolved, what this means is that there are funds locked in this transfer that neither party yet has access to until the transfer dispute window ends, and those funds have not yet been reintroduced back into the core channel state, which is why it's not really possible to say with certainty who those funds are owed to until you call this defund transfer logic. So defund transfer can get called, basically gets called immediately after. Can get called immediately after the transfer is disputed. Actually, I take that back. Okay, let me step through it. So the first thing we do with defund transfer is we pass in the core transfer state. We pass in the encoded initial transfer state. And the encoded initial transfer state maps to the state that's a part of this initial core transfer state. That is a part. Actually, I guess. The nomenclature here is a bit confusing, but this transfer state hash includes the actual full transfer state struct, and then this initial state is a little bit different in that this is the actual state of the transfer logic itself. Let's see if there's a good place where we can point to that. So in this core transfer state, we have these basically these fields that are associated with the transfer overall, and these are for any kind of transfer that you would do. But then within that transfer itself, we have arbitrary state data that is used as part of creating and resolving these conditional transfers, and that is what goes into this initial state hash. And that initial state is actually what is used on chain to resolve a transfer in the event that you don't know who the transfer belongs to. So here we're passing in the encoded transfer state and the encoded transfer resolver. This is basically logic that is used to resolve this transfer in the event of a dispute or in general. and then we get the transfer dispute that already exists. We check to make sure that this dispute has already started, i.e. this defund transfer can only be called after dispute transfer has been called. We verify that the transfer state machine matches the stored one. Effectively, basically, we need to check to make sure that what is passed in over here, the encoded initial transfer state, is what is recorded on chain as part of the dispute. And then we also check to ensure that this is not yet defunded, i.e. you can't defund a transfer multiple times. And we set the transfer dispute is defunded Boolean to true. And then this is actually where the kind of generalized state channel logic comes into play. This is actually the only place where the generalized state channel logic comes into play, which is if the transfer has not yet, the transfer dispute has not yet expired. So there's two cases. Case number one is, Alice disputes her transfer, and Bob has not yet provided a resolving state on chain, and so she disputes her transfer because there are funds in it that she wants to get, and she waits, and she waits until this transfer dispute expiry is finished, and then after that she calls this defund transfer function to get her own funds out. And the other alternative is Alice disputes the transfer on chain for the same reasons, and Bob notices this transfer and says, hey, actually, I do have the means to unlock this transfer. I do have the means to resolve this and get the funds myself. Bob basically is able to call defund transfer before this transfer dispute expiry ends in order to manually progress and resolve the state of the transfer on chain. So this is the case where Bob is progressing and resolving the state on chain. And in this case, we check to make sure that this call is happening from Bob. So basically, Bob is the only person that can actually manually progress the state on chain. And this makes sense because in the event of a dispute, even if you're outsourcing the dispute to a watchtower, you probably don't want the watchtower to submit state progression data on your behalf. That's something where you would want to explicitly be online to do this, because your liveness in this case is a proxy for you having a signature, or for you providing a signature to progress this transfer, which you would have needed if you progressed it on chain. If you progressed it off chain. Then we check to see if the passed in state hash matches. How is this different from? Oh, I see. Sorry, this is not checking the initial transfer state. This is checking the full transfer state hash, and then this is checking the actual initial transfer state. And then we actually do the piece that is kind of generalized and points to arbitrary external logic, which is we call we get the transfer definition from the core transfer state, and then we call the resolve function on that transfer definition, passing in the current core transfer state balance. Basically, this is the balance that's allocated to this transfer, the encoded initial state, and the encoded resolver. And then lastly, we ensure that the balance that you get as a result of this doesn't exceed the initial balances. So this is a sanity check to make sure that whoever implemented the transfer definition contract doesn't accidentally or on purpose try to withdraw more funds than are actually allocated to transfer in the first place. Let's jump in the transfer definition contract, because I think that's otherwise it's going to be a little bit confusing to keep talking about this. So a good example is probably the hash lock transfer. So what a transfer definition is it's a view only contract that takes in it basically defines the state machine for a transfer. It takes in the initial state of a transfer, so the setup params that you have that you create as part of this transfer state struct, and then it takes in a resolver, so i.e. some condition that is some mechanism that is used to unlock this transfer or to complete the transfer to resolve the state machine, and then uses the combination of both of those things to return an updated balance. So jumping into this, the reason that we implement this way is that one of the biggest difficulties of state channels is writing validator logic on chain or off chain. Validator, like you need off-chain validation to ensure that when you sign a message from a counterparty, that message is actually, like you do actually want to sign that. You do want to make sure that you're not inadvertently signing something that causes you to lose funds. However, when you're talking about generalized state channels, doing this is not possible. Like doing this doesn't really scale well if you're having to write new off-chain validation code for every new use case that you want to support. And so what we do instead is we write those validators as basically like as an on-chain contract. We deploy this contract, and it's a view-only contract. We deploy this contract on chain, and then we call this view-only contract as part of the protocol execution. Because it only contains view functions, we don't end up needing to spend any gas to do this validation. However, there is now a global set of validation logic on chain that is very easy to read and everybody can agree on. You get to avoid needing to rewrite all of this code off chain repeatedly. In our transfer definitions, the way that we manage these is we put transfer definitions into a global transfer registry that we control, and this ensures that users are not writing transfer definitions that could inadvertently cause them to lose money. We effectively validate that users are implementing transfer definitions correctly and securely before we allow them to be used by the general network. And we can get in, like that's largely because routers within the network, intermediaries that are forwarding transfers, don't necessarily have context into the lower level transfer definition code. And again, you don't want to end up in a situation where like you're having to rewrite a bunch of validation logic off chain within the routers for every new transfer definition that you support. This is a simple way for us to reduce the complexity of the off-chain code very, very significantly. As part of that registry, we take in the transfer name. We take in the state encodings. So this is the encoding of this transfer state, and then the resolver encoding, which is the encoding of this transfer resolver. And then we implement the create two functions, create and resolve. Create is a helper function. It's never actually called on chain as a part of the adjudication logic or anything like that, but we implement it because this allows us to basically do transfer specific validation off chain without in the same way that I mentioned before, without needing to write custom validation code. This allows us to do it off chain when you're setting up the initial state in the first place and you're creating the transfer. So here, for instance, for a hash lock transfer, we enforce that the recipient balance is not zero, or the recipient balance is zero, i.e. this must be a unidirectional transfer. We enforce that the lock hash that you pass in is not zero either. So there must be something that is actually locking this transfer, and we enforce that the expiry has not if there is an expiry, it has not already expired. And then resolve is the primary function that gets called as part of the dispute logic. So jumping back to the adjudicator, we have this initial state that is registered on chain as part of the dispute transfer. And then when we call defund transfer, if it's being called by Bob before the transfer dispute has expired, the defund transfer function will call the iTransfer definitions resolve function, passing in the initial state, the resolver, and the balance. And this resolve function will take in this call data, implement some sort of check to enforce that this resolver matches against the state and actually is able to resolve the transfer. So in this case, we have the resolver contains a pre-image. We check to see, knocked over some boxes. We check to see if the pre-image matches the generated hash. So the generated hash, basically hashing the pre-image, matches the lock hash that was stored as part of the core state. And if so, then we update the state. And we also have an escape hatch here where if you pass in a pre-image that is byte 0, you can cancel the payment and revert it. That allows you to revert things off chain very quickly and easily if something went wrong. At the end of this, we return balances, the final balances. And in this case, the final balance is, whatever this amount was, this initial balance. The full balance amount has now been transferred over to Bob or to the responder of this transfer. And then we return this balance directly into the defund channel function. And then that balance is used, I guess we save that as part of this this memory variable, and then that balance is used. I guess let's talk about this balance emergency withdrawable, because that's something that we definitely need to cover. So after we have a final balance for both parties, we first call this make balance emergency withdrawable function, and then we emit the transfer defunded event. So what does make balance emergency withdrawable do? Where is that CMC asset? There we go. So make balance emergency withdrawable. So in this case, for each amount within the balance, we make this emergency withdrawable. We first add this to an emergency withdrawable amount mapping, and actually, can you explain this a bit, Heiko?
Yeah, well, the formatting is a bit weird. So this is we only store how much is withdrawable per asset and recipient. And this just adds the amount we have already stored to the new amount and stores it again. So like I said, the formatting is a bit weird. The only interesting thing is this saturated addition. That's a special kind of addition that does not wrap over, nor does it revert in case of an overflow. It just returns the maximum unsigned integer.
Okay, so this is a token overflow protection case.
Yeah, exactly. Yeah, and this has to do with the fact that we talked about earlier, that there could be less actually stored in the multisig than we believe there is, and this is the counterpart, so to speak. So we don't roll over. We saturate it at the maximum amount possible.
Okay, we should definitely put comments on this as well, because this is something that's going to be a bit confusing. Where do we actually execute the transfer itself to withdraw the funds in the event that the transfer gets defunded?
So we only at this place we only store it as withdrawable, and you can.
Oh, we use a withdraw pattern.
Withdraw stuff. Yeah, exactly.
Got it. Okay. Okay, so we store everything as withdrawable, and then we use a withdrawal pattern to allow users to pull their own funds out once they finish completing all of these disputes.
Yeah, exactly.
So we have so that's the defund transfer flow, and then we can jump back into defund channels, since that one's a bit more complicated, and then from there talk about the overarching withdrawal pattern and how a user interacts with that. So defund channel. So defund channel is definitely the most interesting function. Basically, we pass in the core channel state. We pass in the asset ID, an array of asset IDs. The reason we pass in an array of there's a couple of reasons we pass in an array of asset IDs. The first is that it may be the case that you have a lot more assets within the channel than you could defund in a loop within a single call. So this protects against the potential case where your channel state, or the number of assets within your channel state, grows out of control, and your channel state now becomes just like undisputable. In this case, now you could dispute a part of your channel state at a time and still get your funds out. The second reason for this is that it is also possible, there is a case where Bob sends funds within, like, to this channel contract. And because Bob sends funds simply by sending funds to the address, if Bob has sent a token and that token has not yet been reconciled with the off-chain state, then we need to have a new token, which has not yet been reconciled with the off-chain state, i.e. it's not a part of the asset IDs within the off-chain state. That means that Bob disputing, simply defunding the channel without having a record of that would not mean that Bob is able to get those deposited funds out. So there would, i.e. there would effectively be a period of time where neither the off-chain state nor the on-chain state are aware of the fact that this asset ID was added to this contract. And this is just a kind of a consequence of the ERC20 logic. So effectively what we need here in that case is you need to be able to pass in this new asset ID so that the contract, this defund channel function, knows to check for the balance of this new asset ID, even though it's not yet a part of the off-chain state. And then we also pass in indices. I'm assuming that this is just a helper to ensure that basically that the asset IDs in this array can be mapped to the asset IDs that are in the state and the balances that are in the state. Is that correct?
Yeah, exactly. It's just
Cool.
to help. We don't have to run through the entire array and search for the right asset.
Okay, got it. Yeah, so one thing that we do for convenience in the core channel state and the core transfer state is that, actually only in the core channel state, is that we have an array of asset IDs, and then we have similarly have an array of balance objects and an array of process deposits. And all of these are indexed on the same index as the array of asset IDs. And we do this because it keeps it makes the implementation of how we search through the array of balances very simple off-chain, or like at least simpler off-chain, makes it a lot more gas efficient. But of course there is, some additional overhead involved in like dealing with arrays. But yeah, so first things first, we check to see that this that the asset ID length is greater than 0. Effectively we don't want, it removes the possibility that a user calls defund channel by mistake without any asset IDs and then burns a bunch of gas. We also check to make sure that the indices length of this array is the same as the asset ID's array length. That way, well, if they weren't, then this indices array would be completely useless. And then we check to see that basically the channels, the hash of this channel state that is passed in matches the channel state hash on chain, i.e. this channel has been disputed and the state that you're passing in is actually the state that it was disputed with and that was finalized on chain as part of the dispute channel process. And then secondly, we check to make sure, something burning. Is that just the fire? Oh, the fireplace is just, we should close that. So sorry about that. We check to see that the channel is also in the defund phase, i.e. we don't want to allow people to defund the channel when consensus is still being achieved, or when you have basically defunding a previous dispute. We have other checks for this as well. We have a to-do here, beware of reentrancy. It seems like we've already done this, so I guess that's just a cleanup thing. And then we also need to ensure off-chain that all arrays have the same length, which I think we do. Cool. So to defund the assets, what we do is we take the array of asset IDs. We go through each element in this array, take its index, and then ensure that index, the asset ID at that index matches the asset ID that you are currently attempting to defund. and then if the asset that you're defunding is not yet a part of the asset IDs array off chain, this means that this is the case that we talked about where there was a new deposit that occurred. However, that deposit has not yet been reconciled in the off-chain state. And because that deposit was done by Bob, there's no record of it on chain either. And so we need to know that in this case, we are assuming that this asset ID that has an index higher than what exists off chain is a new asset that was deposited as part of the previous that was deposited but hasn't yet been reconciled. So in this case, we check to see if this is a part of any asset that exists, and if it is, then we break. Should we break here? I guess we should, right? Because then in that case, you just
So the logic is you can give indices that help, but you don't have to. So at this place, we have to verify anyway that if it's a new asset that's not part of the off-chain state, we have to verify anyway that it's not one of the assets that are in the off-chain state. And if we have to do that anyway, we can just use this code to find the right asset if the correct index is not given. So currently the indices are optional.
Got it. Okay. Okay, got it. Okay, yeah, that makes sense. Yeah, I was gonna say maybe like I was basically wondering whether it would be a good idea to explicitly revert here, but I think it makes sense to make the indices optional. Like it's really just a convenience thing. So now if index is equal to the number of assets in CCS, then the current asset is not in CCS, otherwise index is the index asset. So at this point, we have a good idea of like what this asset is and what the index of the asset is. And we've checked to make sure that that asset is a part of the state or is a new asset that has not yet been added to the state. Now interesting. Can you explain this a bit more? Open a new block to avoid stack too deep error.
Well, this is just, if we open a new block, this variable, the defund nonce, the UN256 defund nonce gets destroyed at the end of the block, and this one variable was what caused the stack too deep. So that saved us.
That's annoying.
Annoying, but nifty trick, because we always run into
cool
those stack too deep.
Yeah.
Stack too
yeah,
deep.
It's annoying that it was just like one variable that were how many? What is Solidity's limit for that?
Like 19, I think, right?
Oh.
Yeah.
I don't know, in the late teens.
Yeah, it's I think it's even 16, but some count double. So if you have a lot of local variables and some function arguments, you get there pretty quickly, and it can be really annoying to deal with it. So opening a new block for things you only need temporarily is one of the less painful countermeasures.
Yeah, makes sense. Okay, so what we we talked earlier about the defund nonces. We talked earlier about the defund nonces, and that was the idea behind the defund nonces is we want to ensure that we want to make sure that we keep track of the assets that have been defunded as part of a single dispute. And so what we're doing here is enforcing that, is checking to see that these things haven't yet been defunded, and then adding, if they have been defunded, then adding this nonce to defund nonces mapping, and then that way we know that if you call defund channel multiple times within the same defund phase, which you should be allowed to because you are able to pass in your own asset IDs and defund multiple sets of asset IDs over separate calls. In that case, you're not able to, you're not ending up in a situation where you are defunding the same asset IDs multiple times. And secondly, and this is much more importantly because we could make the assumption that if you defund the asset, like 100% of the balance disappears, and at that point, you can't, there wouldn't really be anything to to defund again anyway. But I think the second case here is that you want to avoid potential scenarios where basically, like in the case where we have defunded a channel and now want to restart the channel, we want to keep track of the nonces on chain that each asset ID was defunded at. So in that way, when we restart the channel at a higher nonce in the future with a zero balance, we're not ending up attempting to defund the same value multiple times. And I guess we could talk about, I guess at the end of this call, let's talk a little bit about like how restarting the channel looks and kind of the considerations around that. So defund nonce, let's see. Yeah, so we set the defund nonces, we get the total deposits for Alice and Bob. So this is where we calculate the amounts that have been deposited by Alice and Bob but have not yet been reconciled as part of the state. So get total deposit Alice comes from the on-chain like deposit Alice mapping, and then get total deposits Bob gets calculated using the total amount that has been deposited by Alice, the on-chain current on-chain balance, and the total amount that has been withdrawn. Now we kind of just quickly jumping back here, we do this using we explicitly don't use safe math here because we're using invariant quantities. So this core algorithm, this core difference will always be the same, regardless of whether or not the individual pieces of it overflow or underflow, or specifically regardless of whether deposits Alice overflows. And in fact, we actually want it to overflow, because if it doesn't overflow, and if instead we saturate it, or if we revert, then we could end up in a situation with a channel where you have deposited a lot of funds over a long period of time, you hit the max int, and now your channel becomes undisputable and completely unusable, and whatever funds you have in there at that time are lost, particularly related to a deposit. So I think there's some other documentation around this that we can point to here, but just important to keep in mind that this is a invariant mechanism to calculate the total amount that has been deposited by Bob, using other on-chain properties that we know upfront. And once we have the total amount deposited by Bob, it's easier to calculate what is the amount that is currently owed to Bob for a given asset ID. So off-chain, so we check to see if the current asset is part of the CCS. If it isn't, then whatever balance exists in the contract is refunded back to each party. So in this case, Alice, you would have a record of the amount that Alice has deposited for a new token, say DAI, and then you would have a record for the total amount that Bob has deposited for the same token, and you'd be able to allocate both to each party. And then in the other case where the balance, the asset is a part of the core channel state, but has not yet been included as part of the balance of the core channel state, i.e. you've deposited it, but no updated state has been generated yet. We off-chain keep track of all of the deposits that have been processed so far in the past. And in that case, what we do is we say the total amount of deposits that have been made by Alice subtracted by the processed deposits by Alice must be equal to the balances that are currently outstanding that have not yet been included as part of the state. And those are the balances that now need to be returned back to Alice or Bob. It's a bit, it's kind of nifty. This helps us achieve this property that's highly desirable, which is the two properties which are highly desirable. Property number one is, Bob can basically just send funds into this channel at any time. And property number two, which is actually even more important, is in this case, it typically when depositing or withdrawing from a channel, you either need two on-chain transactions, one to propose the deposit and second to confirm the deposit, or you need two off-chain interactions, one to propose the deposit and the second to confirm the deposit. However, by doing this, we're implicitly we implicitly know which deposits have been proposed or which deposits have been initiated, but not yet confirmed. And so what that means is the off-chain deposit implementation ends up only needing a single round trip. Basically, the way that this now works is Alice or Bob can send funds to the contract at any time. And at some point, doesn't matter when, they can run the deposit protocol to reconcile those new on-chain balances against their off-chain code. You don't need to end up in a situation like we needed to with Indra, where there is some upfront negotiation that has to happen between Alice and Bob before funds can be sent to the contract. Because what we found from experience is that requiring that upfront negotiation means that you're now basically requiring that a user needs to understand that they can only deposit into this address at certain times. And it turns out that that's actually really hard to do. Users will send funds, like if you tell users that this is a deposit address, they will send funds to it at whatever time. And then in the event that you're running a protocol that requires like an off-chain pre-negotiation, sending funds at a time where that off-chain pre-negotiation hasn't occurred results in those funds being lost. So that's kind of the nifty, that's kind of like the property that we get out of this. It's complex and does increase the difficulty of the implementation, but this is like one of the core features of Vector that makes it extremely powerful. And then similarly to what we did with the defund transfers, we make these balances emergency withdrawable and emit the channel defunded event. Cool. So I guess as the final step, let's talk about the withdrawal pattern. How do we actually get funds out of this contract? Is that in? Let's see. Where is that actually?
In ICMC asset.
ICMC asset. Okay, cool. Cool. Or do you mean it's?
Sorry. This is the interface in CMC asset, of course.
Yeah. Okay.
Sorry.
No worries. Cool. So emergency withdraw, or I guess the withdrawal pattern overall. So we set things to be emergency withdrawable, and then we allow them to be withdrawn from the contract. Now this is something that I'm not as familiar with. So Heiko, you might need to help me with explaining how this works and why we have this emergency withdraw function.
So the idea is that we sometimes transfer funds to two different parties. And if you're doing that, there's always the risk that one party could just reject the funds and then your entire transaction reverts, or you have to catch it and go through all sorts of countermeasures to deal with it and make it only for this party, emergency withdrawable, whatever. It really gets complicated, and the general advice from the solidity documentation or from consensus diligence is from the smart contract security best practices to use the withdrawal pattern. So you just store on-chain what can be withdrawn for each party, and in this case also for each asset. And people can then just withdraw it. It's a bit less convenient from a UX perspective. It also requires more transactions, but it's really the safer bet. In fact, we had tried a more complicated approach, and while I believe it worked, the code really turned out ugly and had to deal with many different cases, and we finally decided to go for a withdrawal pattern.
Got it. Okay. And then do we still have the, I guess in this case, I'm assuming that this name has been changed, right? The emergency withdrawal.
Yeah, no one came up with a better name. So it's not really an emergency anymore. But the name stuck around. I think you suggested something with exit.
Yeah.
probably nice, but no one has actually changed it. And yeah.
Okay. Yeah, maybe that's I guess that's something that we can talk about and clean up later today, Lane and I. And then does this also take into account, how does this work with, potential assets that have don't completely adhere to the ERC20 spec? So like, for instance, we talked about Tether.
That's in
that's all handled in this unregistered transfer? Okay. Lib transfer?
asset.
Oh, lib asset. Okay, there we go. Cool. So we have this unregistered transfer function. I see, it's nicely commented. So cool. And then within the transfer ERC20, we use this lib ERC20, and then this takes care of the potential case. This is a wrapped call and takes care of the potential case where the token doesn't fully adhere to the ERC20 spec.
Yeah, exactly.
Cool.
Are
there any like public libraries for this sort of stuff?
I don't think so. This is in fact a little bit more complicated than what other projects like Uniswap use, but this is designed to be the most transparent wrapper around this problem. So it basically works like it only slips in the true value if it's missing, and otherwise passes everything through. So it also tries to, it bubbles up the revert message, what other approaches like the code we had in Intra from Uniswap does not do. However, there is some low-level stuff in this revert if call failed function. So if you do not like it, if you're not uncomfortable with it, you can just replace it with a simpler version, and that should be fine too. This just was meant to be the most transparent wrapper possible.
Got it. Okay, that makes sense. Cool. And then I guess we don't have the we had an emergency withdrawal thing that was used in the event that these calls failed, but now this is no longer necessary at all because we have the withdrawal pattern.
Exactly. Yeah.
Fantastic. Awesome. Well, that's good, because I didn't fully understand the emergency withdrawal stuff before, and I wasn't looking forward to trying to do that. So I'm glad that it no longer exists.
Yeah, the code really had to deal with many different cases because you cannot enforce that an actual transfer succeeds. It could fail for many different reasons. It could fail because the receiver rejects it. It could fail because a central token operator does something weird. And so there are different parties who could have an interest in making this fail, and you have to deal with it in a reasonable way. And that really got tricky and cumbersome, and this is really a much cleaner approach.
Right. Okay. I think this makes sense. I guess the last thing then to talk about is or actually, before we jump into that, do you think there's anything that we've missed as part of this call that we should talk about that's explicitly going to be confusing?
Sorry,
Going to be confusing or should be included in contract updates?
Sorry, maybe a better way to say it is there anything that we have missed as part of this call that you think is an important thing to discuss from like a security or implementation perspective that is like unique to our contracts and will be confusing for auditors?
Off the top of my head, I don't know anything.
Okay, awesome. And then I guess the last thing then is talking about restarting the channel after a dispute has occurred. So this is a really hard problem. It's something that no one really has yet figured out how to do successfully. The idea is that you want to allow for cases where, so first of all, within our implementation, channels are not like kind of, like in many other implementations of channels, many other conceptions of channels, channels are like a throwaway type of structure where you basically create many of them, as many, like very frequently, and like do open and close them explicitly. In our case, a channel is a singular relationship between two peers that have fixed addresses, and that relationship always exists. And so once the way that we implement this is that the channel address is derived using the addresses of both the peers of the channel. So Alice and Bob addresses are the salt that is used to derive the channel, which means that when Alice and Bob interact with each other, they will always have the same channel address. Now, of course, this means that if Alice and Bob get into a dispute with each other, we need to consider the case where the dispute that they get into with each other is for some other reason other than one of the two parties being extremely malicious. And instead, you want to allow for the case where like Alice and Bob may want to continue using their channel after a dispute has occurred. Because if they can't, like if they get into a dispute and that completely trashes the channel, they would never be able to have another relationship with each other again, unless we added some sort of like iterable nonce separately to the implementation as part of the salt. Restarting a channel after a dispute is a pretty critical thing that needs to happen in order for Alice and Bob to continue having a good experience after they have gotten in a dispute with each other. And there's two primary cases where disputes will occur, and we've kind of thought about both of them separately. So the first is, Alice and Bob have a relationship with each other. They may have many transfers open with each other. Those transfers could actually be like multi-hop transfers that are linked to other counterparties down the line, and they need to dispute a transfer. One out of potentially hundreds of transfers, or like a few out of potentially hundreds of transfers, and they don't want to dispute the rest of their channel state. In this case, they would dispute the channel. This would finalize the channel state on chain. In the consensus phase, then in the defund phase, they would dispute the transfers that they want to dispute and defund them explicitly. And then they wouldn't defund the channel. They wouldn't call defund channel. They wouldn't empty out assets from the channel directly. And then the goal here is that then Alice and Bob should be able to sign a higher nonce state that simply removes those transfers from their balances or from their Merkle root, and then continues on normally. So the rest of their channel balance should be the same. The other case is where Alice and Bob, Bob completely goes offline, for instance, or something like that. Basically, communication off chain between Alice and Bob has completely broken down, and Alice and or Bob need to completely exit the channel, in which case they want to defund the channel itself. But subsequently, after exiting the channel, they reconcile, they make up and are friends again, and they want to start the channel again. They want to continue signing new nonces and continue using the channel, basically deposit into the channel again and start using it. This isn't like an unheard of situation. For instance, like if a service provider completely goes offline and has like downtime for a few hours, a user might get frustrated and leave, but then realize, like they could come back and the user could realize, hey, I still want to use this product. In that case, we need to consider, in that case, basically what you're signing as Alice and Bob after the dispute has occurred is a fresh state that has no balances, and is at a higher nonce than anything that has existed before. And then you would go through the process of of depositing funds all over again. So talking about those two use cases, in the former case where we're disputing only transfers, how do we expect this to work currently? I don't know if you guys have a good explanation, but
yeah, I'm not sure whom you're asking, but I don't think that is implemented in any way so far, is it, Lane?
No, it's not implemented, but I noodled on it for longer than before. So sorry, I just didn't hear the question. Can you repeat it?
Oh, yeah, I was asking about, so out of the two cases, case number one being, I want to defund some of my transfers, but not my full channel, and I want to continue operating on chain. And then case number two being, I want to defund the whole channel. What do we do for case number one to restart the channel off chain?
currently we have to do it all manually. Like all of the auto dispute process is like not implemented. You have to manually dispute, which means you also have to manually resolve your channel. That protocol is not implemented. But what you would do is first you would make sure that 0 assets have actually been defunded from the channel. And then once you do that, you would then have to go through and check all of the active transfers that you had. Make sure that your channel state that you have is the latest one that was on chain. If not, get the information from the channel state that was on chain. If you cannot do that, you can't restart your channel. Somebody else has to restart it for you. Like if your store is completely corrupted off chain and your channel's been disputed, you're kind of SOL. Then from there, you need to check all of the active transfers against all of the disputes and make sure that any of the transfers that were disputed and defunded are removed from your channel state. The balance doesn't go back into the off-chain state. It stays like out because it's been transferred out of the multi-sig. You'll also, and then I think that's all you do for case number 1. For case number 2, you don't want to resume off-chain.
Wait. So for case number 1, when are you actually signing the new state? Is it after the entire dispute ends, or is it
It can't be after the entire dispute ends.
right? Because you want to allow for the case where like
What if
your counterparty doesn't countersign that state and you now need to defund your entire channel.
Yeah. So you have to have some buffer of time between when the dispute ends and when you're able to defund things, where you need to get a double signed state back that represents the same one that you sent. If you do not get that within X window, you need to assume that they're being malicious and you have to defund all your assets.
Okay. So one thing that's actually interesting here is like you could have because defunding an asset sets that asset as defunded on chain. There's no possible way to like replay defunding it, like a give, or sorry, not an asset, sorry, defunding a transfer. So there's no way to like actually replay attack defunding a given transfer. So that means that if you have the intention of restarting the channel and like not actually disputing your channel state, as soon as you get into the defund phase, it's actually safe for you to sign an updated channel state that doesn't that simply like has the same channel balances as before and has the same root as before. It's just at a higher nonce, right? And that can be your like quote unquote backup state that you use in case the counterparty doesn't respond to, or like basically in the event that the counterparty does respond and you do want to resume off-chain execution afterwards, that is the quote unquote backup state that you have.
Well, why would you ever want that though? Because like what you're trying to protect against is like, okay, I'm trying to restart off chain, but they literally never respond to me. So even if you sent that chain to them, like state to them with the higher nonce, what if they still just don't respond to you? You have to be able to.
I get that. What I'm saying is like you could actually, because of the fact that you can't replay attack these transfers, it's safe for you to sign an updated state at like basically the exact same state at a higher nonce as soon as you enter the defund phase, because at that point if you sign it and the counterparty doesn't sign, then they don't sign at all for say like 50% of that window, then then you're trying to get, then all you want is to get out of the channel and you could defund your channel. But if they do sign it immediately or at some point within that time period, now it's safe for you to start defunding as many transfers as you want because you have you always have the option of this new state that you can dispute with in the event that your defund window ends. Is that clear? I don't know if that was a clear
Yeah, no, I get what you're saying. I just don't really see the advantage compared to like the complexity that it would add.
I mean, basically what I'm saying here is like, instead of trying to
digging
sign the
into
state
your own
after
mind.
doing all of right. So basically what I'm saying is, instead of trying to sign the state after you do a bunch of things, in which case the time period that you're waiting for a response from the counterparty is dramatically reduced. Instead, you just sign the state immediately. You give yourself the max amount of time where the counterparty is like you're waiting on the counterparty to revert with a message, and then you subsequently also have more time to exit in the event that the counterparty doesn't revert with a message.
Yeah, I guess, but I guess it's weird because even though I guess technically you wouldn't lose attack, or like lose funds in this type of attack, I could always just take that, sign it, hold it myself, wait for you to dispute, defund some stuff, and then like play it myself and try and defund the channel and try and get additional funds out of the channel that way. I don't think it's
You wouldn't be
possible
able
because
to
it
do
would have
that because there's a defund nonce on chain for each asset ID as well.
Yeah, I mean, even if you did, like I said, you wouldn't be able to lose any funds, but yeah, you're right. I mean, I don't know. Like I said, it's like, it seems like there you're just trying to like save yourself what exactly? Like just knowing that your counterparty will be online, but then presumably they will also be online when you send them the signature after you've defunded.
Well, the idea here is just like in general, with all of these timeouts, you want to respond as fast as possible. Like the incentive is to respond as fast as possible because you want to give your counterparty the longest period of time possible. Or maybe a better way to put it is that you want to ensure that you have the longest period of time possible to exit in the event that your counterparty doesn't respond. So I guess the big benefit here is that there's no like downside to doing this. You don't have to like have this new message be conditional upon any transfers that are defunded. You can just have those two things be entirely separate processes, which should simplify the off-chain implementation a lot. But yeah, maybe that's not like super important for now.
Yeah, I'm also not sure how it simplifies the off-chain implementation, because then you have to be aware that like for this type of dispute, my active transfers and my Merkle root are not in line, or like for this type of channel update, which is a weird exception.
Right. Okay. So that's one. So that's what. So I guess that's just for the transfers. So in this case, in the transfer case, basically what we have is, you have you want to sign. You want to make sure that you get a signature from your counterparty that says that they are willing to accept a higher nonce state that has zero channel balances in them, and that has to happen within some period of time before this defund phase ends, because otherwise, it wouldn't be possible for you to subsequently redispute your channel, basically re-empty your channels, right? So like maybe like say like 100 blocks before this phase ends, you want to make sure that you actually dispute your channel if you haven't received an updated state, because at that point you just want to get your funds out.
Right.
And so that's the protection on behalf of like party A, and then on behalf of party B, you have this secondary protection, which is that in the event that this new state is produced, so like say I create a new channel state at nonce number 11, and like the dispute is at nonce number 10, and I sign it, return it to you, and then you subsequently dispute the channel. The secondary protection here is that we store defund nonces on chain, and because we store defund nonces on chain, we know for a fact that you have like my new nonce number 11 state can't be used to try to get those funds out again, can't be used to redispute, because those nonces on chain would not be higher than the nonces that are a part of my state. So that's another good thing, is that we have this protection where we have this kind of bilateral protection where like it's safe for both parties to sign the state, because even if you do defund, all that will cause is a mismatch between the state and what's on chain, but you still won't be able to reuse that state in the future to defund again. And then secondly, we have a similar protection on the transfers themselves, where we check to see if the transfer has already been defunded. And that way, if the new state, so it protects against the case where like I sign a new state at nonce 11 with you, and then subsequently I defund a bunch of transfers to change the on-chain state, change the state of the channel. The on-chain, there would be a check to enforce that those transfers have already been disputed, and you can't like defund them again. Yeah. And then for the other side, so then we have the, what happens in the event that you defund a channel. So in general, what we've said is that if you defund a channel, you should assume at that point that there are no more balances left in the channel, and the next state should be a zero state.
With
that
accepting the asset IDs and the nonce, the defund
right,
nonces.
yeah, right,
without
right.
zero state.
So yeah, sorry, maybe a better way to say it is that you should expect that the balances of the new state at nonce n+1, so this nonce 11 state, are zero. They have to be zero, because if they weren't, then that means that there were funds that were left behind in this channel that shouldn't have been.
Right, and all the process deposits are equal to the total deposits on chain. Like they've all been processed,
reconciled, right?
Yeah.
Yeah. So in that case, it's actually just safe to wait until after the defund window ends to sign this new state, right? You don't actually have to do any coordination within the defund window at all. You can basically just like defund the channel completely, completely exit, and then even pick it back up after a month if you want to, and simply by signing a new quote unquote initial state. I believe that's true.
Yeah, that's correct. I think there's still like a fair amount of edge cases that we have to consider carefully, but I think that it's mostly around case number 1 and like how to make those timing decisions.
Yeah, right. Case number 1 is definitely the more complex one in this case, because we need to think about like whether it is basically, this is completely off-chain question, but like we need to think about when it is safe for us to like sign these new updated states, and how we can, and what those states are.
And what happens if like at the same time I start defunding, somebody sends me back that single sign, like that double sign state.
Right.
Now,
and I guess the other good thing is that in the way that this is implemented right now, if we don't implement the off-chain protocol to sign this updated state, the way that this is implemented right now, you would always just defund the channel. And in that case, you are trashing the channel moving on, but at least like we capture this base case safely, where you're not, it's not like we are leaving, it doesn't seem like we're leaving any open holes as a result of us wanting to allow for this new use case in the future.
Yeah, I mean, we're not limiting it on the contracts side, and I don't think we've left any big security holes, but I think that like our understanding of how to safely do it might change a bit. Like it's not set in stone, but that's all off-chain stuff.
Okay, that makes sense. Cool. I think that's probably good. In general, this looks really good.